Hello, my name is David, and I and my partner Marachuku will be presenting on the design of a solar powered system for green hydrogen production in Kano State, Nigeria. We will be utilizing MATLAB and Homer softwares. Here we have our table of content, and we will be going through each and every one of them during the course of our presentation. There has been a substantial surge in interest in green hydrogen, particularly after the thanks to the commitment of countries to achieving net zero. Now, hydrogen is very important as it has been recognized as a strategic carrier of energy compared to traditional fossil fuels. Also, it is also renewable. Now, to achieve this goal in our project, we focused on using Homer software, the hybrid optimization model for electrical renewables, also called Homer. This For our report, we will delve into the world of electrolyzers and electrolysis, and we will employ the use of PEM electrolyzers, which are proton exchange membrane electrolyzers, highlighting their adaptability and importance in carrying out the process of generating pure hydrogen, pure green hydrogen. Now, as it stands, energy is a cornerstone for any nation's societal advancement or economic advancement. This fact has prompted intensified global researchers to address the concerns surrounding our current dwindling fossil fuel reserves and supplies. Also, climate change is of important concern to these researchers. In Nigeria, the population is rising and growing and currently has approximately 218 million people. Uh, Yet, fossil fuel is the main source of energy. So, of course, we are presently with this work trying to reduce Nigeria's dependence on fossil fuels theoretically by generating green hydrogen and reducing its increasing CO2 emissions and encourage the underuse or underutilization of renewable energy resources. Uh, as it stands, Kano State, located in northern Nigeria, currently holds significant economic and, of course, cultural importance and significance. It is a relatively large state with over 2,000 square kilometers. Solar results that are obtained from NASA via the Homer software to informs this study. And from figure 3 here, we can observe that there is a notable temperature disparity between the months as during the course of the year, with highlighting April as and May as the warmest months at 30.9 degrees Celsius, and January as the coldest or coolest at 21.6 degrees Celsius. Now, figure 4 here shows the monthly solar irradiation for our chosen study location, uh, varying from 5.218 kilowatt hours per meter square per day in January to up to 6.364 kilowatt hours per meter square per day in May, averaging about 5.9 kilowatt hours per meter square per day annually due to seasonal changes. Now, also, basic components we used include power converters, solar panels, storage, batteries, and of course, electrical load.
Good evening, everyone. Just like my partner David has stated, there are four major components of our design system. The electrical load is primarily the energy demand in our study location, Kano State of Nigeria, and it basically makes up of the housing appliances, the low industrial loads, and street bulbs, and all of that. And we were able to study the pattern of energy demand in the community over a period of time, and we were able to come up with a graph as we see in figure 6. In summary, we see that the average demand of this community is about 860 kilowatt hour per day with a peak load of 96 kilowatts. The major component of our design system, which is a solar panel, as we know, it depends on the power that this solar panel is going to generate, depends on the size of the panel, the solar irradiance, and the ambient temperature. We looked at these factors and we were able to come up with the CSCX325P solar panel as specified in the HOMA software. This panel has a 20 kilowatt rating and a 25-year lifespan. The other component, which is the converter, is a bimodal component in the sense that it functions either as a rectifier or as an inverter depending on the demand. As a rectifier, when we need to charge up the battery, we need to convert AC current to DC to charge up the battery, or as an inverter when we need electrical AC power. So this is going to convert DC to AC. The next component is the battery, which we serve as a buffer in the sense that it will store excess energy from our solar panel, and we will also be able to supply the load to the community and also to our hydrogen plant. We also need to look at the electrolyzer itself, which is the component that is going to generate hydrogen. We're able to come up with a model where we have the electrode area of 0.25 meters square, the rate of feed as 1000 kilomole per hour, the operating temperature 90 degrees, the number of electrons per reaction as 2. So basically this electrolyzer, when electrical current is passed through it, the electrolyte is going to break down into ions, with the hydroxide ion moving towards the cathode and the oxygen ion moving towards the anode. From this figure 7, we see that from our Aspen, we were able to come up with a piping and instrumentation diagram for the water electrolysis process. So basically this diagram is just showing us the process flow from when the water is introduced into the hydrogen plant and passing through the following processes, and at the end of the day we are left with hydrogen and oxygen gases, which with hydrogen gases being our main focus. We look at the results of our analysis and we see that the optimal energy system for this our design is going to comprise of 293 kilowatt of solar panels power rating, with 603 strings of battery and about 155 kilowatt of power converter. The cost analysis showed that the total cost, net present cost of this our system is going to cost about $786,000, with a levelized cost of about $0.194 per kilowatt hour. So in this other result and discussion, we see that just like I earlier stated, the piping and instrumentation diagram of our electrolyzer requires some form of control. So here we see the results of about 4 types of control. The first being the system running as an open controller, and from figures 8 depicts that. We can see the nature of the graph there. The next form of controller we can use for this our electrolyzer is the proportional controller. Here we see that the KP value of 1.1 to 50 yields a rise time of 0.27 seconds with an amplitude of 0.847. Here we see that this is a better form of controller compared to the open control because we have some settling time and we have a minimal overshoot, but it also has some inadequacies. We go to the other type of here we have the proportional integral controller. This controller, from the results and the graph, we see that it yields about a rise time of about 0.486 seconds and an amplitude of 1.31 with an overshoot of 30%. So yeah, this controller brings the system to the set point with minimal rise and settling time, but it falls short in controlling the overshoot. Thus, this type of controller, it is unsuitable for our electrolyzer. The final form of controller is the proportional integral derivative controller, which yields a rise time of 0.58 seconds and an amplitude of 1, and it has no overshoot. So this form of controller is the best fit for our electrolyzer system. In conclusion, our analysis shows that renewable energy offer a very efficient solution to our energy demands in the country, especially in Kano State. So, but in order to harness this potential or this solution within a proper technical economic study needs to be done, which we have just done. And from our analysis and study, we see that this solar hybrid system can generate electricity as well as produce electricity for green hydrogen production with a total cost of approximately 786,000 and a levelized cost of $0.194 per kilowatt hour. Also, from our MATLAB analysis, we see that there are various forms of controller, but the PID, which is a proportional integral derivative controller, proved to be the optimal controller for our PAM electrolyzer as against the other forms of controllers. Thank you.